Hello everyone, I hope you're all doing well and that you and your families are safe during these challenging times. My name is Hassan Termos and today we'll be working through a few problems as practice for the upcoming quiz 1 in EECE330. This session, it's part of an initiative by the Cultural Club of the South, and it's meant to support you and help you study, especially given the immense stress and the academic load caused by the war that has been forced upon us. I believe this session will be highly beneficial for a lot of you. What we did is we carefully reviewed past exams from ECE 330, from previous offerings of ECE 330, and we've selected questions that we believe will best prepare you for your quiz. Our goal today is not just to provide solutions to problems, it's actually to walk you through the problem solving process so you could approach and solve similar problems confidently. And with that, let's begin. We're gonna create a new project in Visual Studio and we'll start with the first problem. Problem 1. Dynamic array pop. Consider the code you're given for dynamic arrays in dynamic-array.h. So this is the given file, dynamic-array.h. What I'm gonna do is I'm gonna create a new file, call it dynamic-array.h, but I'm gonna create it within the Visual Studio project. So this is a new header file, dynamic-array.h, and I'm gonna open this file in Notepad, copy all of its content, and paste it in this new file I created. Okay. Let's start with part A. Implement the copy constructor. Explain in comments what could go wrong if there is no copy constructor. So, as you probably know, the copy constructor takes as arguments, actually takes a single argument of type dynamic array in this case. We're gonna copy the size as we normally would, copy the capacity, okay, but for data it's not gonna be enough to just do something like this. This wouldn't do what we actually wanted to do. So what we're gonna have to do, and I'm gonna explain why in a minute, is we're gonna have to allocate a block of memory of size capacity, and we're gonna have data point to this new block of memory, and then we're gonna copy element by element. We're gonna copy every element in other.data into this new object's data attribute. So it's gonna look something like this: new data array of size capacity, and then we're gonna loop over other.data, and we're gonna copy element by element into data. Okay, so why do we have to do this? Or rather, why do we have to define a copy constructor in the first place? So the idea is, if we don't define a copy constructor, then what the C++ compiler does is it provides a default constructor, a default copy constructor. And what this copy constructor does is it performs a shallow copy of all the member variables. So it's gonna perform a shallow copy of size, a shallow copy of capacity, and a shallow copy of data. So functionally it would be kind of equivalent to what I showed you earlier, which was this. It would kind of be functionally equivalent to this. And why would this cause issues? This causes problems because it could potentially lead to double freeze. For example, say we create a dynamic array of integers, call it d1, and we populate this dynamic array we insert some elements. Let's say we inserted 9 and 10, and then we create a new dynamic array, and this is where the problem starts to show itself. And we create this new dynamic array d2 by invoking the copy constructor on d1. So now d2 is a dynamic array that was created through the copy constructor and by basically copying d1. And remember, here we're assuming that we didn't define this new explicit copy constructor, and we're relying on the implicit copy constructor provided by the C++ compiler, which would functionally act similar to this. So what's gonna happen is that d2's size is gonna be a shallow copy of d1's size. This isn't really an issue. And the same thing with capacity. d2's capacity is gonna be a shallow copy of d1's capacity. The problem is that d2's data attribute is gonna be a shallow copy of d1's data attribute. This means that those two pointers basically point to the same block of memory, to the same location in memory. And why would this cause an issue? Because when ultimately these two dynamic arrays go out of scope, one of them is going to get destructed. Let's say d2 gets destructed, then d2.data is going to be freed. This block of memory is going to be freed, and basically we lost it. So when d1's destructor gets called after that, or gets invoked after that, we're gonna attempt to free the same exact block of memory. So we're basically trying to free the same block of memory twice, which is basically a memory issue. So this is why a copy constructor is important. This is why we can't perform a shallow copy of data like what's being done here. To recap, the issue is that if we perform a shallow copy of data, d1.data and d2.data would be pointing to the same block of memory. So when one of them gets destructed, this block of memory is freed. So when the other one gets destructed, this is when the issue happens. When the other one gets destructed, we're gonna be attempting to free the same block of memory twice, which is a memory issue. This is why we have to do this. We have to create separate blocks of memory for each dynamic array's data attribute, and we're gonna have them point to those separate blocks of memory, and then we're gonna copy the data one by one. Hopefully this clarifies part A. Okay, now as for part B, implement a member function pop, which removes the last element of the array. If the size becomes less than capacity over 2, so that's strictly less than capacity over 2, then the allocated memory for the array should shrink by a factor of 2. That is, capacity becomes capacity over 2. Okay, this is kind of similar to insert, where in insert, if we need extra space to insert a new element, we double the size of the array. Here, it's basically when you remove an element. If you remove too many elements and the array is too empty, quote unquote, then we would have to shrink the size of the array. So let's see this in an example. Let's say we start with an empty array, so size would be 0, and capacity, now the default is 16, but let's say we override this default and set the capacity to let's say 1. So now let's say we add an element, we add the element 1, so size would be 1, and capacity is not gonna have to double or increase in any way, so it's gonna stay at 1. Now say we add a new element, now size is gonna be incremented by 1 and capacity is gonna double. Oh sorry, size is gonna be incremented by 1 and capacity is gonna be doubled. Now say we add another element, let's say 9, then size again is going to be incremented, and capacity again is going to have to be doubled. Now let's say we remove 9. So we're going to end up with something like this. Here capacity is not going to change because we're asked to have capacity change if the size becomes strictly less than capacity over 2. Here it's equal to capacity over 2. So capacity is not going to change. But if we remove 2, then we're going to end up with an array of size 1. And here capacity is going to have to be divided by 2. So the idea is whenever size is less than capacity over 2, we're going to have to divide the capacity by 2. This could introduce some memory advantages, because if you imagine we have an array that we added a lot of elements to and then we removed a lot of elements, then if we keep capacity at a large value, then we might be wasting space. So that's why this could be useful. Anyways, let's implement this. So they didn't specify that we need a return value for pop, so we will just make it void pop. And here we have this edge case that we can take care of right off the bat, which is if the size is equal to 0. So if the size is 0, then we could just silently ignore this, or we could assert that the size is greater than 0. So these are two ways of dealing with the edge case where size is equal to 0. So what assert does here, or what assert does in general, is that if you pass in a boolean value to assert, then it checks this boolean. If it's true, then nothing happens. If it's false, then it aborts the program. It halts your program. So basically what this is doing is it's checking if size is greater than 0, then all is fine. We just continue executing whatever we're gonna write under it. But if size is not greater than 0, then the program is gonna halt. This function, the entire program is gonna stop executing. So yeah, we have those two options. Assert is kind of more aggressive. We're stopping the entire program, while here we're just stopping the function. We could also check if size is less than 0, but generally we're probably gonna make sure this doesn't even happen. But for now, we could go with this or with the other option, which was assert that size is greater than 0. Now we're gonna remove the element. So first we're gonna remove the element, and then check if by removing the element size became less than capacity over 2. If size became less than capacity over 2, then we're gonna have to somehow divide the capacity by 2, and this would mean shrinking the array. And if not, so if true, so if size is less than capacity over 2, then somehow shrink the array. If it's not true, then just do nothing. We removed the element, so we're good. Okay, so first, how are we gonna remove the element? This could simply be done by decrementing the size. So why is this enough? This is enough because when we decrement the size, then later on, if for any reason we're looping over the elements of this dynamic array, then since the size is decremented, so okay, let's illustrate this through an example. So here the size was 3. If we decrement the size and we keep 9 there, like it's still there in memory, but the size is 2. So if you loop over the array, or you want to do anything with the elements of the array, then you're gonna stop at the second element, since the size is 2. So even though 9 is there in memory, so it is kind of there, but you're not gonna ever reach it it's kind of like you could consider a garbage value. So it's there in memory, but size is too small for us to reach it. It's similar to whatever is here in memory. When capacity is 4 and size is 3, whatever is here is part of the allocated block of memory. It's part of the memory that belongs to our dynamic array, but we're never gonna reach it since size is 3. So in a similar sense, we could just decrement size, and now we're never gonna reach 9. We could consider it a garbage value at that point. So it's enough to just decrement size, and this would basically have the effect of removing the element. So it's still there in memory, but we're not reaching it, so we can basically consider it removed. Now we have to check if size is less than capacity over 2. So if size became less than capacity over 2, then now we're gonna have to somehow shrink the array, and otherwise we're done. So now we're gonna have to fill this if statement. So what are we gonna have to do? The game plan is, first create a new actually allocate a new block of memory to replace data. Let me maximize this. Okay, so we're gonna create a new block of memory. We're gonna allocate a new block of memory to replace data, and then we're gonna copy all the elements from data to this new block. Let's call this new block new data. So we're gonna copy the elements from data to new data, and then we're gonna carefully and very carefully replace data with new data. So it's kind of similar to what we do in insert, where we create a new block of we allocate a new block of memory, and it's basically the same thing, but the difference is that here the new block of memory is double the size, but in our case it's gonna be half of the size. So let's see how this is done exactly. So first of all, we're gonna allocate a new chunk of data, which is gonna be a chunk of data of type t, and the size of this new array is gonna be capacity over 2. And as a reminder, here we have a t pointer and not t, since whenever you use new, what you get is a pointer to a block of memory of this type. So we're gonna have to store it in a t pointer variable and not just a t variable. And then after we've created this new block of memory, or after we've allocated this new block of memory, we're gonna loop over the elements in data. Oh, I forgot a semicolon here. Okay, so we're gonna loop over the elements in data, and we're gonna copy them over to new data. So new data at I is equal to data at I. And now we're gonna have to replace data with new data. We can't just do this. This would lead to a memory leak. Why would this lead to a memory leak? Because if we do this, then whatever chunk of memory data used to point to is now inaccessible, and we can't access it to delete it. So if data used to point to a chunk of memory at address, let's say 123, now data points to a chunk of memory at address whatever new address new data was given. So let's say it was 987. So now data points, after this line, data is gonna point to this new address, and this old address is lost. So we have no way of getting to this address and deleting it, and to free this memory. So this leads to a memory leak. So what we're gonna have to do is first delete data, Actually, we're gonna have to delete data using this syntax, since it points to an array and not just a single element. And then we could say data is equal to new data safely, since whatever chunk of memory data used to point to is already freed. And now we just have to divide capacity by 2 and everything would be done. So to recap, we first have to allocate a new block of memory, and then copy the data from copy the elements from data to this new block of memory. Then we have to delete data, and then we can have data point to this new block of memory, and then we have to divide capacity by 2 just so we make sure all our member variables are consistent. So two things. Firstly, regarding this is syntax that I use when not that I personally use, but that's generally used when talking about addresses. It's 0x and then the hexadecimal representation of the address. Don't worry about it too much. It's basically just, this is some address, this is another address that data would be pointing to after this operation. Regarding delete, the name might be a bit misleading. What delete does is it deallocates wherever block of memory data is pointing to. So say that before this delete line, data used to point to a block of memory that say contains 5 integers. What this delete line does is we're basically just deallocating that chunk of memory. We're no longer reserving it. So the term deleting the pointer may be a bit misleading. The pointer is fine. We can still use it later on, and we actually do use it. We set data equal to new data. But what really happens is that whatever chunk of memory data is pointing to is now deallocated. And yeah, I think this is the end of problem 1, and yeah. Okay, now on to problem 2, database of companies. For this problem, you are given 2 CPP files which contain some test code. For parts A through E, you will submit one file. For part F, please submit a separate file. Okay, so these are the provided skeleton files. These are the files for problem 2. p2f.cpp is meant for part F, so we're not gonna concern ourselves with it for now. p2a.cpp is the one we care about right now. I opened it in Notepad and I copied all of its content, just like I did with dynamic_array.h. I'm gonna create a new item, call it p2a.cpp, and paste the content here. And since I'm done with dynamic_array.h, I'm gonna remove it. Note that I'm removing and not deleting. We're gonna remove it, so it's removed from the list of source files on the right. As you can see, I only have p2a.cpp now. Okay, let's go back to the problem statement. Suppose you work at the Ministry of Labor and want to create a database of companies. As such, you will create a class company which has the following member variables: a private pointer to a string, EMPL, standing for employee, which will be used to store the names of the employees of the company, and 3 public member variables: a string name for the name of the company, an int num for the number of employees, and an int capital to denote the company's worth. So this is fairly straightforward. You just have to create a class called company. We have one private member variable, which is a string pointer EMPL. We have 3 public member variables: a string name, an integer num, and an integer capital. Now note from the description of the string pointer, the problem statement states that it will be used to store the names of the employees of the company. So this string pointer, it looks like it will be pointing to an array of strings rather than a single string object. It seems that EMPL will point to an array of string objects where every element in this array corresponds to the name of a single employee. This should be clear as we advance through the problem though. Now let's continue reading the problem statement. For full grade and proper functioning of your code, you may need to implement additional functions that are not explicitly stated below. This is a very, very important note. The idea is that even though your code may seem correct, it may run fine on the given test code, but it is not considered 100% correct or 100% functional unless you tie some loose ends. So there may be some functions that you have to implement even though the problem statement doesn't explicitly ask you to implement them. I know I'm being kind of vague. I don't want to reveal what those functions are just yet. Be on the lookout for them, try to find them, try to figure out what they are and how you would implement them. And by the end of the problem, hopefully everything will be clear and you'll know what those functions are. Now let's go to part A. Create a constructor for class company which takes 4 arguments. 2 integers to initialize capital and num, 1 string to initialize name, and a string array to initialize EMPL. That is, you will use the pointer EMPL to dynamically allocate an array of strings of proper size and set its elements according to the input argument. So it's very important to understand our member variables. Here, capital and num and name, it's kind of obvious what they each represent, but for EMPL it's worth it to take a moment and be sure that we understand what EMPL is used for. So now it's much clearer that EMPL is used to point to an array of strings rather than a single string object. More specifically, it's used to point to a dynamically allocated array of strings where every string represents the name of a single employee. Let's implement this constructor. Since it's a constructor, we'll start with the name of the class, which is company, and notice that the order the arguments are mentioned in the problem statement is 2 integers, then a string, then the array of strings, but in the test code it's the string, then the 2 integers, then the array of strings. So we'll stick to the order in the test code. Let's start with the string to initialize the value of name. We have an integer for capital and an integer for num and a string array for the for EMPL. So dealing with name is fairly straightforward. Dealing with capital is straightforward as well. Dealing with num is straightforward as well. And dealing with EMPL is similar to dealing with the data pointer back from problem 1 when we were implementing the copy constructor. So doing this is not enough. If we do this, then what would happen is that EMPL would just point to E in memory, and that's not the effect that we want. What we want is for EMPL to point to a dynamically allocated array, and the values in this dynamically allocated array would come from the array E, but they would be separate. EMPL should point to its own separate array. So what we have to do is similar to what we did in problem 1. We're going to have to dynamically allocate an array of strings and have EMPL point to it. Now the question is, what should the size of this array be? So in other words, we have this dynamically allocated array that contains the names of our employees, and we're asking what size should this array be. Now this may be obvious to some of you that the array should be of size num. Why? Since num is the number of employees. But this highlights an important concept. It's important to understand the relationships between the member variables. So EMPL is a pointer to an array that contains the names of our employees, and num is the number of employees. So it's natural that the size of this array that EMPL is pointing to should be num. Now note that we can't just write num here, since num is not considered initialized as long as we're still within the initializer list. So we're gonna have to use n, which is basically the same value that we need. Now after that, similar to what we did in problem 1, we're gonna have to loop over the elements in E and set EMPL at I equal to E at I. And by the way, this assignment operator for strings, it copies the string. So EMPL at I and E at I are different, separate copies of the same string, but they're not really the same object. So now EMPL and E are completely separated. They do have the same values, but they're separated in memory. Okay, now on to part B, or actually before we go on to part B, let's test what we've implemented so far. Let's comment the portions of the test code that we're not ready to run yet. We've only implemented the constructor, the first constructor so far, so let's run this. Let's run our code. And perfect, it runs without any errors. The exit code is 0, so it looks like everything is fine. Let's go on to part B. Part B, create a default constructor which sets name to no name and sets capital and num to 0. So this is fairly straightforward. We have a default constructor. A default constructor is a constructor that takes no arguments. We're gonna set name to no name, and we're gonna set capital to 0, and we're gonna set num to 0. Perfect. On to part C, overload the insertion operator to print a variable of type company. So we want to be able to run a line of code like this and have this output. Now notice that this insertion operator, the way it runs, or the way it's invoked, is that we have an object of type OStream. Cout is an object of type OStream, and then the insertion operator, and then an object of type company in this case. And recall that usually when you invoke a binary operator, it's invoked through the object on the left hand side. So this insertion operator is invoked through cout, which is an object of type OStream. Since this operator is being invoked through an object of type OStream and not an object of type company, it doesn't make sense to overload this operator from within the company class as we normally would. As we'll see later, we could overload it from within the company class, but it's slightly different than how we would normally overload an operator related to our custom class. So the idea is, if we have some operator, for example, let's say we're overloading the addition operator. If we have a company object plus another company object, for example, then this operator is going to be invoked through the object on the left hand side. So it's going to be invoked through an object of type company. So it makes complete sense to overload it from within the company class, and that's what we do. But since here the left hand side, the object on the left hand side is not of type company, then we can't just normally overload it like we would overload the addition operator. I'm gonna build up how we overload this operator. In an exam setting, you would probably just go with one of the final versions I'm gonna show you, but I'm gonna go through this step by step. So let's start with let's start with ignoring the return type. Let's just set the return type to 0. So when you do cout and then the insertion operator and then some object of type company, what we're gonna do is we're just gonna return nothing. So it's gonna be void operator insertion, or the symbol of the insertion operator, and then it's gonna take two arguments. First the left hand side and then the right hand side. So the first argument is gonna be an argument of type OStream, let's call it O for example, and the second argument is an object of type company. Let's maximize this. Okay, so what we're gonna do is we're gonna invoke the insertion operator on O with the company object c.name. So we want to first print the name. Let's look at the output structure again. Okay, we have name, and then a new line. Okay. And then we're gonna have to print out the capital. And then the number of employees. For now, let's ignore printing the names of the employees and let's focus on printing the name, capital, and number of employees. So let's go back to our implementation, take another look at it, and try to make it better. So we're overloading the insertion operator. We have two arguments, an OStream reference O and an object of type company C. We're printing the name, capital, and number of employees. So let's try to test this implementation and then try to improve it. So it seems to be functional. So the first improvement that one might notice is that this parameter C is a copy of the argument ballot. The details behind this is that the default behavior in C++ is passing by value. So when you call a function or invoke an operator, the argument by default is passed by value, meaning that C would be a copy of ballot that's generated by invoking the copy constructor on ballot. That's the default behavior in C++. And you might notice that we haven't defined a copy constructor, but what's being used here is the implicit copy constructor that's provided by the C++ compiler. So this behavior of copying the input argument is not really needed in our case. We don't really want to copy ballot and create a copy C and then use C. We could just use ballot, and in fact that could be more efficient because we're avoiding an extra process which is copying. So to avoid this behavior, the way to do that is make C a reference to a company object instead of making it just a company object. So what's gonna happen now is, since C is a reference, what's gonna happen is that when ballot is passed in, C is gonna become a reference to ballot. So they're gonna be referencing the same object in memory rather than C being a copy. Another improvement that one might notice is that we're not really altering C within this function. So the member variables of C are not being altered. They're being accessed only to print them out, but they're not being changed. So what we could do is make C constant. What this keyword does is we're basically telling the compiler that we're not gonna change C within this function. So we're not gonna do something like this. We're telling the compiler that we're not gonna do something like this. And in fact now the compiler would raise an error if we try to do this. And we're also not going to be calling any function that does something like this. So we're not going to be directly nor indirectly changing C or its member variables. So these are the first two improvements that we notice. One other thing that you might notice is that the return type here is void. So we wouldn't be able to do something like this. Let's break this down. The way C++ evaluates such an expression is from left to right. So first it evaluates this part, and then it evaluates this part. So let's try to go through this step by step. First, we're calling the insertion operator through cout on balut. So this function is gonna run, and the return type is void. So this will be evaluated to void. And then we're gonna try to call the insertion operator through void on end L. But it doesn't make sense to call the insertion operator, or any operator for that matter, through void. So this would raise an error because this expression is going to be evaluated to void, and we're trying to invoke an operator through void on end L. So how do we get around this? One way to get around this is to have this expression evaluate to the OStream object that was passed in the first place, which is cout. So when we passed in this OStream reference object O, we could change the return type to be OStream reference and return this object. So now this evaluates to basically cout, and we're couting end L, or we're calling the insertion operator through cout on end L. So now it doesn't cause any issue. So to recap, when this was void, the problem is that this expression is going to evaluate to void, and now we're doing void, then the insertion operator, then end L, which doesn't make a lot of sense. We wouldn't invoke an operator through void. So the way we got around this is by returning the OStream reference object that was passed in the first place, and then we're using it as the left hand side for this binary operator. So now this evaluates to cout, and we're doing cout, then the insertion operator, then end L, which is okay. Hopefully this makes sense. So this will be the last version we'll cover of overloading the insertion operator to print out the name, capital, and number of employees. Now the next step we're gonna take is print out the names of the employees. So the way we could do this is through a simple loop. We'll loop over the EMPL array, or the array pointed to by EMPL, and we'll do something like this and put a space after the name of every employee. You might notice the red squiggly line under EMPL, which signifies that there's an error of some sort. Hovering over EMPL shows us that the error is that the member company EMPL declared at line 6 is inaccessible. What does that mean? So this member variable is inaccessible. You might see the issue right away that EMPL is private, and this function is defined outside the class company, so it doesn't have access to the private member variables of company. So how do we get around this? One way to get around this is by letting the compiler know that we want to allow this function to gain access to the private member variables of our class. The way we do this is inside the class, we'll use the friend keyword followed by the signature of the function and a semicolon. This line tells the compiler that we're giving access to this function. We're giving it access to our private member variables. So now this function is allowed to access EMPL even though it's a private member variable. So notice that there's no red squiggly line anymore, and if we remove this line that we added and try to test the code using the original test code, if we run this now, everything seems to be functional. So this is the first option you have. You could tell the compiler from within the class that I want to give this function access to my private member variables, and then define the function outside the class, or you could define it within the class. So right after you include this statement with the function signature, you could add the function body, and it seems to be functional. Also, one note about the friend keyword: if you declare a function as a friend, then you'd be giving it access to not only the private member variables but also the protected member variables. And so yeah, in an exam setting, you're probably best off with one of those two options: either this, where you declare the function as a friend and provide the body right away, or you declare it as a friend but provide the body outside of the class. So it would look something like this. The body is provided outside the class, but you declare it as a friend inside the class. Yeah, so you'd probably go with one of those two options. So I believe part C ends with this. Now on to part D. Write a member function find, which given a string returns true if the string corresponds to the name of an employee and returns false otherwise. So let's implement this as a simple linear search. First, this function returns true or false, so the return type is Boolean. Its name is find. It takes a single string as an argument, and let's just loop over the elements in EMPL. And if EMPL at I is equal to S, we return true. Otherwise, only when the for loop finishes executing without finding any employee whose name is S, only then do we return false. And based on what we discussed previously regarding this parameter, we could also have this parameter take on this structure and try to justify this based on how we justified this parameter taking on this structure. So additionally, one other thing that we could do is we could add the keyword const here. So we're adding the keyword const between the argument list and the function body of a function that's within a class. When we do this, we're basically telling the compiler that this function will not change the state of the object that it's being called through. So for example here, we're calling find through the balut object. Since we added the keyword const here, then we're telling the compiler that find will not alter the state of balut, which is true in this case. We are using some member variables, but we are not changing them. We're only using them in comparisons, so they're not being changed. This ends part D. Now on to part E. Write a member function acquire, which when called via a company B on another company C, first checks if the available capital of B is bigger than the capital of C. If not, it returns false. If yes, B acquires C in the following sense: all the employees and capital of C are moved to B, C's name is updated by appending the word closed, and other member variables are updated accordingly. So let's take a look at the examples. Here we're defining a new company called Olympus, which has only one employee, Zeus. And if balut attempts to acquire Olympus, then it would fail and we would return false, as you could see in the output here. However, if Olympus attempts to acquire balut, then it would succeed, we would return true, and the capital of balut, which is 1000, would be added to the capital of Olympus, which is 10,000. So now Olympus would have a capital of 11,000. Additionally, the employees of balut would move to Olympus. So now Olympus would have 3 employees: Zeus, Sami, and Samia. Sami and Samia being the employees that belonged to the company balut. And the name of balut would have closed appended to it. Its capital would go down to 0 since it was moved to Olympus, and the number of employees goes down to 0 as they were also moved to Olympus. So this may seem like a complicated task at first, but let's just break it down into manageable chunks and tackle it from there. So let's start defining this function. First of all, it returns either true or false. So its return type is boolean, its name is acquire, and it takes as input a single company, let's call it C. So notice here that we might actually alter the state of C. So we don't want to have it passed in as a constant. No, we might actually want to change the state of C. And here it's actually very important that we pass C as a reference. It's not only a performance issue here. The thing is, if we pass, if in this example, balut is passed by copy or by value, then we'll be altering the state of the copy. So our changes wouldn't really reflect on balut. And that's not what we want. We want to actually change the original balut object, so we want it to be passed by reference. And notice that we don't need to pass both objects as parameters, because we're calling the acquire function through one of the objects. So here we're calling acquire through Olymp. So we already have access to the member variables of Olymp. But if we try to access the variable num, this is num, which is the member variable of Olymp. If we want to access the member variables of balut, for example, we'd have to do something like c.num. So anyways, let's start implementing the logic. First, we'll take care of the trivial case. So we'll check if capital is less than or equal to c.capital. So basically we're checking, if we're taking this call as an example, we're checking if the capital of Olympus is less than or equal to the capital of balut, then Olympus can't acquire balut. So we'll just return false, and that would end the function. Otherwise, if Olympus's capital is greater than the capital of balut, then first of all we'll add the capital of balut to the capital of Olympus, and then we'll set the capital of balut to 0. So now balut's capital has been transferred to Olympus, and the name of balut will have closed appended to it. So now we've taken care of capital and name. Now we still have to take care of num and the EMPL. So we'll take care of them simultaneously. First of all, let's define a variable total employees, which is the number of total employees that Olympus is going to have after it acquires balut. So initially we might naively assume that the number of total employees that Olympus is going to have is num plus c.num. And let's go with this for now, and then we'll see why this is not entirely true, and we'll edit our code accordingly. So now we're gonna have to figure out a way to transfer the employees from balut to Olymp. So what I'm gonna write here is not gonna be strict C++ syntax, and I'm not gonna be using strict C++ terminology, but I'm just gonna try to get the point across. The idea is, initially we have let's call it a list EMPL of names, and we have a list C.EMPL also of names. And what we want by the end is we want EMPL to be equal, so we're going to do some operation, and then we want EMPL to be equal to the concatenation of these lists. So how are we going to achieve this? This is going to be kind of similar in some parts to what we did in problem 1 with the dynamic array pop. So what we're going to do is, first we're going to define a new EMPL list, so-called list, and it's going to be of 3 empty strings. So in this example it's 3, but in general it would be total EMPL, total employees. The size of it would be total employees. And then we're gonna go through an intermediate step where we copy the elements from EMPL to new EMPL, and then we're gonna copy the elements from c.empl to EMPL to new EMPL, and then carefully we want to make EMPL point to the same chunk of memory that new EMPL is pointing to. And I say carefully because we have to avoid memory leaks. And this is very important. So this is the game plan. Now let's try to implement it. What we're gonna do is, first, new EMPL is gonna be a pointer to a string. It's gonna point to a dynamically allocated chunk of memory of size total EMPL. New EMPL should be a string pointer that points to a chunk of memory that could store a total EMPL number of strings. And then we're gonna start copying the employee names. So we've reached here. We're gonna try to copy the employee names from EMPL to new EMPL. And we're gonna do something like new EMPL is at I is equal to EMPL at I. So at this point we've reached this intermediate step. Now we want to copy the elements from c.empl to new EMPL, and we're gonna loop over the elements in c.empl, so we have to be careful that the size is c.num and not num. So new EMPL at I is equal to c.empl at I. Now what I've written here is not entirely correct, because what do you think is going to happen here? We have this list and we start looping over this list, and we're setting new EMPL at I equal to c.empl at I. What's going to happen is we're going to accidentally overwrite Zeus. So we're going to start at index 0 and copy Sammy over, the name Sammy over, and then we're going to go to Samia, and then the loop will end. So the issue is we don't want to start copying, we don't want to copy the ith element in c.empl onto the ith spot in new EMPL. We want the ith element in c.empl to be copied to a spot, to the spot starting from where EMPL stopped being copied. So to clarify, if EMPL took the first spot, so we want to start copying c.empl from the second spot onwards. Or more generally, since EMPL is going to occupy the first num spots, we want c.empl to start occupying the spots from num onwards. So instead of copying c.empl at I to new EMPL at I, we copy it to new EMPL at I plus num. So at the first iteration, we're copying c.empl at 0 to new EMPL at 0 plus num. So we're starting the copying process from this position. So as not to overwrite the employees copied from the EMPL array. So now new EMPL contains the data that we want it to contain. So now we start the careful process of making EMPL point to where new EMPL is pointing. So the question is, can we now safely delete EMPL? And the answer is yes. We've already copied the data we need from it, so it's safe to delete. And the same thing applies to c.empl. Sorry, this is a typo. And now we set EMPL to point to the same place where new EMPL is pointing, and the number of employees for this company is going to be equal to what we calculated to be the total number of employees. And then for C, the number of employees is going to be 0, and it could be a good idea to have C.empl be equal to null, just to be safe, so that no one would accidentally try to access some employee that belongs to C, because we've already transferred them all to the other company. And finally, it's a good idea to return true. Actually, we should return true to signal that the acquiring process was done successfully. So hopefully this is clear. And now I want to go back to this assumption that we made. We assumed that total EMPL is equal to num plus C.num, which this assumption might hold for the given example. Let's actually run this and test it. Yeah, we should be fine now to run the entire test code. Okay, so this is going well. This piece of this part of the output is from the previous runs. This is from Balut trying to acquire Olymp. This is actually, sorry, this isn't from the previous runs, it's from the examples that we've already covered. This is from Balut trying to acquire Olymp. This is from Olymp trying to acquire Balut. So Balut didn't succeed, Olymp succeeded. Now Olymp, the name of Olymp was didn't change. Its capital increased by 1,000. The number of employees became 3. The employees are Zeus, Sami, and Samia. The name of Balut, it seems I've missed a space here. I'll just add it now. And its capital of Z is 0, and the number of employees is 0. So it seems everything is functional. I should just add the space here. Okay. Now let's take another example. Let's say that Zeus works at both companies. So what do you think would happen here? So let's try to run this. So it seems oh, sorry, this should be changed to 3. Okay. So now it seems like Zeus was viewed as was counted twice, because he used to work at both companies. So when they were acquired, the assumption we're making is that the new number of employees should be equal to the sum of the number of employees, but we're ignoring the possibility of an employee belonging to both companies before one acquires the other. In this case, as you can see, the problem is that this employee would be counted twice. So to solve this issue, it's actually not very straightforward. But here's one solution. Here's how we can alter the logic of our present implementation to include a solution for such a case. So what we could do is the total number of employees, instead of it being num plus C.num, it could become num plus C.num minus the number of, let's call them repeated employees or common employees. So the idea is, if an employee is repeated in both lists, we want to subtract the number of such employees so that they're counted only once. And then while we're copying the names of the employees, we want to be careful that every name is copied only once. So here's how we'll do this. First of all, we're gonna want to count the number of repeated employees. So let's say int repeated employees is equal to 0. to count the number of repeated employees, what we're gonna do is we're gonna loop over the employees of Olympus. Let's take that as an example, and we're gonna check for every employee in Olympus, check if you can find it as an employee in the other company, which is Ballout. So this so we're looping over every employee in Olympus, checking if we can find it as an employee in the other company in Ballout, and if we can, we increment the number of repeated employees. So by the end of this loop, we would have counted the number of all repeated employees. Hopefully this makes sense. We're looping over the employees of Olympus. For each one, we're checking if it appears as an employee. Sorry, we're looping over the employees of Olympus, yeah, and we're checking for each one if it appears as an employee for Ballout, and if it does, we increment the counter, and at the end, the total number of employees is the sum of the number of employees of each company minus the number of common employees. And now this portion of the code is gonna have to be edited significantly. So let's comment this out. Actually, let's copy the elements from EMPL. So copy the names of the employees from Olympus, and then while copying the names of employees from Ballout, we're gonna try to be careful to not copy the name of an employee that has already been copied. So let's keep track of the number of employees that we've already added so far. So this serves this could serve multiple purposes, but one important purpose that it serves is it tells us the index at which the next employee should be added. So the next employee should be added at the index num. That's an important purpose of this variable. And now we loop over the, actually we could make use of this for loop. So we're looping over the employees of Ballout, and we'll check if c.empl at I, if the current employee cannot be found as an employee in the list of Olympus. So we're looping over the list of employees for Ballout. For every employee, if it cannot be found as an employee for Olympus, we're for an employee for Olympus before the acquiring process began. So if it can't be found, then it's a new employee for Olympus. So we're gonna add it. We're gonna actually copy it. So new EMPL at added is equal to c.empl at I. And this is where added is useful, because here added told us that the next employee, the new employee, should be added at this index, and we're gonna increment added. So the next employee will be added one index ahead. So basically added keeps track of where the first empty slot is. So after we copy Zeus, added would have a value of 1 because the first empty slot is at index 1. And then after we add Sammy, after we add Sammy, then added will have a value of 2 because the first empty slot is at index 2. So basically this would keep running until we go over all the employees of c.empl, and we copy all the ones that we haven't previously seen in EMPL. And the rest is basically the same. The memory management bit is basically the same. We still just have to carefully replace the old EMPL list with the new one. So now let's run this example. So this example, remember, it includes this repeated employee. And our program now takes care of this example without repeating the employee. Let's revert this back to what it was. And then let's go through a high-level recap of what this function is doing. First, we take care of the trivial case, then we update the things that are easy to update. We count the number of repeated employees, then we calculate the number of total employees, taking into consideration that some employees may have been repeated. Then we copy the employee names from the list of Olympus to the new list, and then we copy the employee names from Balut's list to the new list. But before copying every employee, we make sure that this employee hasn't been copied before as an employee of Olympus. And then we do the memory management stuff. So now, before we go to part F, I want to go over this important note that I highlighted at the beginning of solving this problem. And at this point you may have noticed that I skipped a very important part of this class, or maybe you're noticing it now, but we have no destructor, and this is a big problem. So this memory that we're allocating and having EMPL point to, this memory has been causing memory leaks. This allocation of memory has been causing memory leaks all along. So what we're gonna have to do is implement a destructor basically, and this is how we'll do that. So the syntax for implementing a destructor is this tilde followed by the class name, and it's very simple. What we want to do in this destructor, we want to deallocate the block of memory that EMPL is pointing to. So this very simple destructor is what stands between completely functioning code and code with memory leaks. So this for this problem, I believe this is the only additional function that we have to implement, at least for this problem up to part E. This should be the only additional function that we have to implement without being explicitly asked to do so. In problem F, you might see one or two, I guess, functions like that. So anyways, let's go to part F. So for this part, we're gonna need the new skeleton, p2f.cpp. So let's open this in Notepad, copy the entire file, create a new file, call it p2f.cpp, paste everything here, and notice that now, because we have two files with a main function in them, we are forced to remove one of them, because Visual Studio, we're basically gonna get errors if we don't remove one of them. So make sure to remove the one you're not working on. For now, I'm gonna leave them because we might need to copy something from P2A to P2F. But when you want to start running your code, be sure to remove the one you don't want to run. So now, part F. In the first part of the problem, we assumed that employees array consists of strings. Different companies, however, might store the data of their employees in a different way, say with more information than just their names. In this part, you are asked to modify company to make it a template class, so as to provide support for different types other than string. For instance, you are provided with an incomplete class person which has two private member variables, string name and an int ID. So this is p2f.cpp. This is the class that the problem statement is mentioning. We consider ID to be a unique identifier of a person, i.e. two persons with different names but the same ID are in fact the same person. For example, if the name is Ibrahim Isa and the ID is this value, it would be the same person as I Isa with the same value for the ID. Now part F. Update company and person so that the same functionalities implemented above work correctly. Example code is given in the file p2f.cpp. Note, you may assume that acquire will only take arguments of the same type. That is, if Balut is of type company string and olymp2 is of type company person, then we will never call balut.acquire olymp2 nor olymp2.acquire balut. Okay, so let's dive right into this. So what does it mean to template a class? The idea behind templating a class is, say you created a certain class that's, for example, this company class we just created. It's meant to deal with cases where the employee, the information on employees are stored in an array of strings. So say later on we want to store employee information in an array of person objects. We could rewrite the entire class to adapt it to person objects, but what if later on we want to switch to another class or another class after that? We can't keep rewriting the company class over and over. So the idea is to generalize the company class so that whatever type we choose, we could plug it in and the company class would adapt to it. So this is the idea behind templating. Now let's see it in action on this company class. So first we're gonna copy our code, including the overloading of the insertion operator. And here to avoid complications, it might actually be a better idea to go with the option where the insertion operator is within the class, because when you template the class, this operator would be templated, would be basically templated as part of the process of templating the class. So let's start. The way you start this is by adding this line. This would tell C++ that the class below is templated. This T here is the type parameter. It's basically a placeholder for what type the user is going to choose. So for example, if later on someone wants to use your class and instead of string they want EMPL to be an array of type person, they would pass in person as the value for T. So T is the type parameter. It's the type that the user of your class chose. So we will write the company class sort of in terms of T, so that later on whatever T is chosen, the class can adapt to that. Of course, assuming T adheres to some constraints that we're gonna talk about in a moment. So let's start going over the class and changing whatever needs to be changed. So we're gonna change EMPL from being a pointer to a string array to being a pointer to an array of objects of type T. So whatever type the user specifies and passes in as a value for the type parameter, then EMPL would be a pointer to that. As for name, there's no need to change it. We're not required to change every string, every occurrence of string to T. We're only required to change whatever has to be changed, so that we're allowing employee data to be stored in different formats, and the name of the company has nothing to do with that. Int num and int capital don't have to be changed. As for this constructor, string NA is used to initialize the value of name, so it doesn't need to be changed. The same with int C and int N, they're being used to initialize capital and num, so no need to change them. As for string E array, it's being used to like we're copying data from it into EMPL, so it only makes sense for it to be an array of type T objects. And as for EMPL, it's gonna have to point to an allocated block of memory, so we're gonna have to allocate the block of memory with the type T in mind. So we're allocating an array of size n that holds type T objects. As for the body of the constructor, no need to change anything there. As for the destructor, no need to change anything there. As for the default constructor, there is no need to change anything there. For the insertion operator, here it's kind of implicit that company is company T. So it doesn't. It might be a good idea to include the T there, just to make it very clear that outside, like in most contexts outside this class, company is no longer a well-defined type. When we template this class, a well-defined type would be company, and then we specify a value for the type parameter. But without specifying the value for the type parameter, it's ambiguous what type we mean. But while we're within the class, it's kind of implicitly understood that company is company T. So within the class we're keeping it in terms of T, and it's implicit even if we don't really type it. As for find, let's go over the logic here. We used to pass in a string, and we used to loop over EMPL and check if any element in EMPL is equal to that string. So now it makes sense that we have to pass in an element of type T. So instead of const string reference, it's const T reference now. As for acquire, we still have to acquire a company, so the type is not going to change here. And also here it might be a good idea to keep this to make it clear that we're only accepting input of type company when the path parameter is set to a value of T, meaning we're not going to accept any company as input to this function. We want to accept companies where the path parameter is set to the same value as that of the company we're calling the function through. So basically what I'm trying to say is, as the problem statement explained, we don't want to allow a company where employee information are stored as strings to acquire a company where employee information are stored as person objects, for example. We want T to be consistent between those two. Otherwise, as for the body, this portion I don't believe is gonna need to be changed. Neither does this line need to be changed. Here, new EMPL, instead of being a string pointer, it's gonna have to be a T pointer. Otherwise, I believe the company class is okay now. Let's test this portion of the test code. I think we could run everything up to this point. Okay, so everything seems to be functional. Okay, so now let's see what needs to be changed in the person class so that it could be passed as a value for this type parameter. So as I mentioned before, there are some constraints that we are requiring for the types that could be passed as values for this type parameter. For example, one of those constraints may be subtle, and you may have to run your program and try to figure out what the error is trying to tell you so that you can catch them all. But I'll point one out. For example, here in the find function, we're checking if EMPL at I is equal to S. So EMPL at I is of type T and S is of type T. So we're kind of implicitly requiring T to define an equality operator. So it might be very subtle, but we are requiring something from T here. And depending on what version of C++ you're running, the compiler may not give you a default equality operator, or if it does, it might not be the equality operator that we need, which is based on the ID. So anyways, we're gonna have to define this. So this should be fairly straightforward. It returns a boolean, so we'll write it this way, or overload it actually this way. It's gonna take as input a const person reference, let's call it P, and I'm adding the keyword const and the reference symbol because one, I don't plan on changing the member variables of this person object, and two, I don't care for the person object to be copied. And simply we would return ID is equal to p.id. So what other constraints are we requiring or are we enforcing on those types that are passed as values for the type parameter? Let's try to run the code and see what could pop up. Now one thing that pops up right away is that apparently we need a constructor that takes the name and then the ID. So let's implement that. So we have a constructor, we're gonna have person, it's gonna take string n, int I, and initialize name to n, and ID to I. So this should take care of these. Oh, it seems I've put the constructor in the wrong place. It's set as private, but the constructor should be public. So this takes care of these. Let's try to run the code. Okay, so we got some errors. Let's see what the errors are trying to tell us. So person, no appropriate default constructor available. So if we go to line 98, it's t pointer new EMPL is equal to new array of objects of type T of size total EMPL. So it doesn't seem there's an obvious call to the default constructor, but recall that when you allocate a block of memory of type T, every object in that block is initialized based on the default constructor. So there is an implicit call to the default constructor here. So we're gonna have to define a default constructor for person, and for now maybe we could just leave it empty. Let's try to run this code again, and we get another error. No operator found which takes right hand operand of type T. So this is on line 54. So on line 54 here we're overloading the insertion operator for the company class, and at this point we're printing out, or we're invoking the insertion operator through O on this object c.empl at I, which is of type T. So it seems that we're also implicitly requiring this type T to have overloaded the insertion operator. So the idea here is we're printing c.empl at I. So we're assuming that c.empl at I is of a type that's overloaded the insertion operator. And since this type could be person, so we have to overload the insertion operator in person. So as you notice, there's a lot of requirements that we weren't explicitly asked to implement them as part of the problem statement, but because person is required to be a valid value for the type parameter, then these requirements naturally pop up. So we're gonna have to overload this insertion operator. So let's do this. We have friend ostream reference, and then operator insertion ostream reference ostr and const person reference p, and let's let's use the format that was used in the problem statement, which was this, and then some ID. So we're gonna do OSTR this, then open parentheses and open quotations, and then the name, then close quotations and the comma and space, and then the ID, and then close parentheses. And yeah, we should access those through P, since this is not a member function, even though it's defined inside the class, but it's not a member function. It's only declared as a friend. So now let's try to run the code, and we get other errors. Oh, the operator must return a value. I forgot to return OSTR here. Okay, and now it runs. So to find those errors, sometimes it's easier to just run the code and see what errors come up and then try to fix them accordingly. Because, for example, to sniff out this, for example, it would have been really difficult to figure out that there is a hidden call to the default constructor here. It wouldn't have been very easy to spot. So it's a very important skill to have, to be able to get errors, read them, understand them, and try to act upon them. So yeah, and notice here in one of those examples, this Olymp2 object, it has two, it's represented as having two employees, Poseidon and Hades. Hades has an ID of 3, and then this under object also has Hades as an employee. So notice that we correctly dealt with this case and only included Hades once. So even if you didn't in this problem, even if you didn't notice that you have to deal with the case where employees are repeated when you did part E, in part F you would have noticed it because of Hades being repeated. So yeah, I believe this brings us to the end of problem 2.